As we know, a chip is made from sand. After melting, we can get an ingot by a sieving method. And ingot will be cut into pieces, and we get a wafer. Then we do the front-end process and the wafer, such as lithography, ion implantation, annealing, and so on. Then we cut the wafer into small pieces, and we get a chip or a die. The last step is to package and protect the chip. And this is also called the back-end process. Each piece we cut from the wafer is called a die, and only the very outermost surface, several microns of the die, is fabricated with devices and structures, and the bottom is nothing but silicon. The surface structure of the die is like this. The bottom is CMOS structure with source, drain, and gate. This is called FEOL, the front end of line. And the upper part is copper interconnect made by dual damascene process. This is the BEOL, the back end of line. Copper interconnect ranges from local to intermediate and global, from nanometer scale to micrometer scale. And the part directly contact with CMOS is called contact. It is also for interconnect, but it is always made by tungsten or perhaps cobalt. All of this is called the front end of IC production. And the following step to connect the die to the world outside is called back end or electronic packaging. That includes soldering, bonding, thermal management, and so on. So a die is cut from a wafer and then attached to a package substrate, then covered with a metal lid. Then we get a packaged chip. This chip will be put on a PCB board to connect with other components, such as memories, capacitors, resistors, and so on, to be a system, such as a PC or a smartphone. So we know for a chip to connect with the world outside, there are 3 layers in a basic structure: a die, a package substrate, and a PCB board, sometimes called a motherboard. This part is called manufacturing, or the front end. It is wafer level, and the main material is silicon. Its technology is with nanometer scale resolution, and the companies dedicated on this part include TSMC from Taiwan, Intel from United States, and Samsung from South Korea, and SMIC from China. This part is called packaging, or the back end. It is chip level, or sometimes package level. The main material of the package substrate is ceramic or polymer. Its resolution is micrometer scale, and the companies include ASE in Taiwan, Anko in United States, and JSET in China. The last part is called assembling, or system level, sometimes called board level. The main material of PCB board is polymer, and its interconnect resolution is millimeter scale. SCC is the largest PCB board provider in the world, and Foxconn performs assembling for many system-level customers. Chip-scale packaging is about how did the die connect with the package substrate. There are 2 typical methods: wire bonding and flip chip. In the case of wire bonding, a bonding wire made of copper or gold is used to connect the copper trace and the surface of the die and the copper pad of a substrate. In the case of flip chip, the die is inverted upside down, and a solder ball is used to connect the copper trace and the copper pad. At the beginning, Only when the chip is inverted will the soldered ball be used. However, afterwards, TSV is inverted, so the die can be connected to the substrate by solder balls even without being flip chipped, but this method will also be called as flip chip. For flip chip, there are two different ways, FCBGA and FCCSP. The former usually has more I/O numbers and larger package size, which indicates it has a stronger calculation performance. In this case, the die is protected by a metal lid, and thermal interface materials is required to fill the gap between the die and the metal lid. In case of FCCSP, the die is protected by molding compound if the chip do not suffer serious thermal problems. In both cases, underfill material is needed to fill the space between solder balls because the coefficient of thermal expansion between the die and the substrate are quite different, and underfill is needed to release the stress concentrated on solder balls. Similar to the feature size of front-end CMOS structure, the solder ball size and pitch are shrinking simultaneously, from C4 bump to lead-free bump, and then copper pinna and micro pinna. As we discussed, for a chip to connect with the world outside, there are three layers in a basic structure: a die, a package substrate, and a PCB board. To make a system like a smartphone or a PC, the different components needed to be integrated, such as memory, logic, passive devices, and so on. This work is normally performed on a PCB level, and it is called assembling a system on PCB. Sometimes it can be done on package level to put different dies on one package substrate. This is called system in package or SIP. The most advanced method to do this in wafer level. To put all the components in one single die, this is called system on chip or SoC. We've discussed the chip scale packaging. Now we're going to introduce wafer-level packaging. In short, wafer-level packaging is to use something of the front end to do packaging that normally done in the back end. I think we can consider this concept from two different ways. The first one is to use part of silicon wafer for packaging. A typical example of this concept is CoWoS of TSMC. Chip and wafer and substrate. An additional layer or a wafer is added between the die and the substrate. This layer is made of silicon. The different dies are connected with each other by the wires in this wafer. And because it is a silicon wafer, so the wires can be fabricated using the front-end process. Thus, its resolution can be much thinner than normal package substrate for high-density interconnects. Another example is EMIB of Intel, embedded multi-die interconnect bridge. A silicon bridge die is embedded in the package substrate, and similarly, these wires in the bridge die are much thinner than a normal package substrate. A very interesting point of EMIB is the bump size in one die can be different. The larger solder balls directly connect to the package substrate, and smaller bumps are connected to the bridge die and further connect with other dies. Another way to consider wafer-level packaging is this packaging is performed at wafer size. Now, this method is basically based on the redistribution layer technology, normally include both fan-in and fan-out. We will talk about this point later. Here we see a word, chiplet. So what is a chiplet? A chiplet means a small module die. We introduced a concept that a single die integrated many components such as CPU, memory, and so on. It is called monolithic chip. Actually, this is SoC we introduced before. On the contrast, we may just make many simple modular dies with certain functions. These dies are fabricated at different technology nodes, 7 nano, 14 nano, 28 nano, and so on. Actually, we can make a chiplet library with a lot of standardized chiplets, and the customers can mix and match the chiplets and connect them, just like assembling Lego parts into a system. The chiplets could be connected using existing package types, such as 2.5D, 3D, and fan-out. Here we mentioned 2.5D and 3D. What was that? We introduced CoWoS and EMIB a while ago. Both of them are 2.5D packaging. It seems there are 2 layers of silicon die stacked horizontally. However, the interposer wafer and the bridge die are not real dies. They do not have their own logic. They are only used for interconnects. They are not active. That's why they are only regarded as half of a die. So both of the 2 methods are called 2.5D. And 3D IC means you must have at least 2 layers of real die stacking. And normally, a TSV is required to connect the both sides of a die. This idea has been proposed by Richard Feynman in the 1980s. He said that another direction of improvement is to make physical machines 3-dimensional instead of all on the surface of a chip. Here we show a 3D IC with stacked chips, and the chips are connected by bumps. And when you see bumps, you need anti-film materials. So 3D ICs can be done by 2-layer stacking that include chip-to-chip, chip-to-wafer, and wafer-to-wafer. Here we show another 3D IC, Foveros of Intel. This structure looks very similar to that of CoWoS, chip and wafer and substrate. But unlike CoWoS, the interposer layer here is active with the ON logic built in. It uses thousands of micro bumps to realize face-to-face interconnect. So this is 3D IC. Both EMIB and Foveros are from Intel, and they have combined both techniques to make a new one, called EMIB. As we said in EMIB, larger bumps direct connect to the package substrate, and smaller bumps are connected to the bridge die and further connected with other dies. In Foveros, an active interposer is used to realize face-to-face interconnect with dies. And in this co-EMIB, the active interposers here are connected to this in-bridge, to this EMIB bridge die. At current age, most 3D ICs are realized by a TSV to connect both sides of a die. Before TSV is widely used, there are some other methods. One is to use bonding wires to connect a smaller die a larger die, and an even larger substrate. Another method is to use flip chip, a daughter die flip chip to a mother die, and then flip chip to a grandma die, and then flip chip to a package substrate. Both of these above two methods have shortcomings. First, the sizes of the dies must increase gradually, a smaller one to a larger one, and then an even larger one. The second problem is only the edges of the die is used for input-output interconnects, and the central part are not used. Then we can note the benefits of TSV. The sizes of the die can be very uniform, and the I/O bumps can be everywhere of the die, even in the central part. That increases the I/O density. TSV must succeed for 3D IC, or we may see this very weird structure. In 3D IC, the end of TSV is a micro bump. Then the bumps are bonded together using a flip chip method, and when you have bumps, you will need end fill. But end fill is not good for thermal conduction. So a new concept is proposed, SOIC, where it is bumpless, and no bumps means no end fill. The concept of SOIC is proposed by TSMC. It is generally a front-end wafer process. It is achieved by direct bonding. This is the interface of stacking layers, copper to copper, silicon to silicon, and somewhere oxide to oxide, directly bonded. Direct bonding is also called surface-activated bonding. It requires ultra-clean and ultra-flat surface treatment. This is originally proposed by Professor Suga of the University of Tokyo. The next part we're going to talk about fan-out. Fan-out wafer-level packaging. You need to first cut the silicon wafer into pieces of dies. After that, you assemble the dies together and molding them to be a new wafer. Then you fabricate redistribution layers, or RDL, to make the interconnects between different dies and connect to the world outside. There can be several layers of RDL. The finest wires connect to the chip, and the broader wires connect to the solder balls. There are two very important package materials in this process: liquid molding compound, used to mold the dies into a new wafer; photosensitive polyimide, or PSPI. On one side, it is used as photoresist to fabricate patterns for copper interconnects. On the other side, it is used as no-K dielectrics and will be preserved in the product. This page shows schematically the process of fan-out process. There are two different ways: molding first and RDL first. In the molding first mode, there are two different types. The first one is face up. The chips are upside down. The first one is face down. The chips are upside down, inversely mounted in a carrier by some tape. Then molding compound is used to mold a new wafer, and then the carrier is released and then fabricate RDL layers. The second is face up. The chips are normally assembled in a wafer, and then molding, and then polish the top molding and expose the bumps. Then fabricate RDL layers and plant solder balls. The difference is bumps are necessary in this face-up method. Otherwise, the structures and the chip may be damaged during this polishing process. The other method, RDL first. RDL is directly fabricated in the carrier and then have cap traces on the top. And then the chips are mounted in the carrier with RDL, and then molding, and then release the carrier, and then solder balls. We've introduced the process of fan-out. You may be interested in what is fan-in. Both fan-in and fan-out are based on RDL process, where the difference is in fan-in, the RDL traces and solder balls are routed inward just below the area of the chip. Here the blue region indicates the chip size. In fan-out, the RDL traces and solder balls are routed both inward and outward. The RDL and solder balls can be made on molding compounds. The advantage of fan-out, it allows ball placement beyond the die area, which indicates you can have higher I/O density. Besides, it can be used for interconnects between different dies, which allows it to be a technique for system-in-package and heterogeneous integration. This we will discuss later. Fan-in is also called wafer-level chip-scale packaging. Wafer-level means this technique is based on the RDL process performed in a wafer size. Chip scale means the final product, the final chip, is a chip scale. Fan-in wafer-level chip-scale packaging technology provides a solder interconnection between chip and motherboard directly without packaging substrate. Package-on-package is another method for system integration. TSMC presented this info POP structure to connect memory and logic devices, where the logic chip is packaged by fan-out and the memory chip is stacked on the package below. The both sides of info structure are connected by this through info wire, or sometimes called through molding wire. This info POP method has a thinner profile and better electrical and thermal performance because of the absence of packaging substrate and C4 bumps. POP structure is widely used in smartphone chips. This figure presented the cross-sectional polished structure of Apple, Samsung, and HiSilicon, or Huawei, presented by Bill Chen of ASE in an EPS webinar. The structure of Apple A12 showing here is not very easy to understand, and I found another picture in this year's ECTC conference presented by Eric Bain from iMac. We know that both Apple and Huawei requires TSMC to make chips for them. And this figure from TSMC in an ECTC proceedings can explain their structures. In the case of Apple A12, this memory chips is connected to the two-layer laminate or package substrate by bonding wires, and the wire is connected to a solder ball and then a through info wire. This SoC chip is packaged by fan-out. The through info wire is connected to the redistribution layer and then to the BGA balls, and finally to the bottom PCB board. In the case of HiSilicon, the memory is connected to the two-layer laminate by bonding wires, and then connected to the solder ball, and then the solder ball further connected to another two-layer laminate on the top, then connected to the bottom four-layer laminate using through molding wire. The SoC chip is connected to this package substrate using flip chip method. Here we can see very small micro bumps. And then the substrate is connected to the PCB board using BGA balls. In the following part, we will show some package structure related with fan-out in this year's ECTC conference. This one is system on wafer from TSMC. That is, the molded wafer is the system with different modules, and there are 6 layers of RDL. 1, 2, 3 have 5 micron width and pitch for chip-to-chip interconnect, and 4 to 6 have 15-20 micron width and pitch for power distribution and other connections. The advantage is this structure do not require a PCB board and can be directly connected to a power distribution module, and it has a higher line density and a bandwidth density. In this page, we introduce fan-out wafer-level packaging for gallium nitride from Fraunhofer. We know that gallium nitride is a wide bandgap semiconductor and can be used at high temperature conditions. A thermal sink is attached with this gallium nitride chip. The copper pad is attached to the die with silver sinter adhesive. The backside of gallium nitride is deposited with gold, or this is called backside metallization. And the fan-out process is conducted with copper pad. The gallium nitride die with copper pad molded together, and then polish the backside to expose the copper pad, and then RDL, and then solder balls, similar to a normal fan-out method. This page shows fan-out FOIP from Spill, which is another top packaging company in Taiwan. Here, the technology of fan-out and embedded die are combined together. Generally speaking, this fan-out process is performed on bridge dies rather than normally active dies. Firstly, bridge dies are molded together and then fan-out and interconnect with each other. Then the output of fan-out is bumps. The active dies, such as SoC chip and high bandwidth memory dies, are connected to the bumps using flip chip method, and fill, and then all of these are molded together to attach to a package substrate. This method is useful for producing high-density interconnects using embedded die and RDL, and it is very flexible for mass-die integration. In this page, we are going to introduce embedded glass fan-out, EGFO, presented by Shanwen Yuntian, a Chinese company on wafer-level packaging. Glass is used as the substrate wafer, and it is a simple technology without temporary bonding and debonding process in the fan-out process. Perhaps it will have lower dielectric loss for high-frequency operation. The chips are embedded in a glass wafer frame. Then molding compound is used to fill the space between them. Then RDL and fan-out for the interconnects. Another technology used here is through glass wire to connect the antenna patch with chips. We can see the fan-out solder balls and RDL, and we can see the antenna arrays used here. Then panel level packaging. What we talked here is fan-out panel level packaging, but not assembling on PCB level. There's some kind of related. Many years ago, Fraunhofer studied how to embed dies into PCB board rather than attach them on the surface. Afterwards, they developed fan-out wafer-level packaging, and then they combined these two ideas together and defined fan-out panel-level packaging. If you can have 2 micron Now in space, an organic substrate, it is no longer a PCB board, but something else. We denote it at panel-level packaging. We know that when we put rectangular dies in a round-shaped wafer, we lose some area. So why don't just use a rectangular board for packaging? By using panel-level packaging, apparently, the package efficiency is much higher than wafer level, because it can be done in a much larger size and no space is wasted. In this page, we show the 3D interconnect landscape. It is presented by Eric Bain from IMEC. It shows that the 3D interconnect at different levels: package, die, wafer, and transistor. Actually, we have discussed them earlier. Package and package stacking, this is actually the PLP we introduced. 2.5D and embedded die, we've introduced CoWoS and EMIB. And then 3D IC with bumps, and then SOIC using direct bonding, wafer-to-wafer bonding, and ultimate 3D IC, CMOS transistor stacking, which is perhaps the most advanced technology, but also the most expensive. Next, we're going to talk about the roadmaps for semiconductor technology. The roadmaps guide the semiconductor industry development. Used to be ITRS, now it is changed to HIR, Heterogeneous Integration Roadmap. In 1991, the National Technology Roadmap for Semiconductors is sponsored by U.S. Semiconductor Industry Association. And 7 years later, in 1998, the NTRS expanded to ITRS, and Europe, Japan, Taiwan, and South Korea joined. About 2 years later, in 2014, the benefits of Moore's law scaling is diminishing, and ITRS is ending. In 2016, they issued the last edition of ITRS. In 2014, ITRS Heterogeneous Integration Team signed a document initiating the formation of Heterogeneous Integration Roadmap, and it is funded by IEEE, EPS, EDS, Photonics Society, SEMI, and a package division of ASME. It is going to embrace innovation wherever possible to accelerate progress in microelectronics market landscape. The main part of ITRS is CMOS shrinking, or the front-end process. Everything must get adapted to it. However, this road is hard to go, as we know that after the 14 and 10 nano technology, it is very expensive and very difficult to make it further shrinking. The Vice President of TSMC, Dr. Yu, predicted that the SOC approach inherited ITRS will lead to higher cost with the development of technology node, and the effect of material and structural innovation is not that good as well. The only way to continuously reduce the cost might be heterogeneous integration. So, what is heterogeneous integration? Bill Chen of ASE gives a definition: to integrate die and many heterogeneous components to be a system in package. And it is heterogeneous by materials. You may have silicon, gallium nitride, gallium arsenide, polymer, ceramics, glass, metal, and so on. And it may be heterogeneous by component types. You will have resistors, inductors, capacitors. And it will be heterogeneous by circuit types, logic, memory, or MEMS. Heterogeneous by technology node, You may have 28 nano, 14 nano, 10 nano, 7 nano, whatever. And it can be heterogeneous by bonding or interconnect method. Flip chip, wire bonding, 2.5D, 3D, fan out, and so on. Please notice that the concept shape we used here is much more diverse rather than merely put different dies on one package substrate as we introduced earlier. The concept we mentioned here, the package include fan-out, embedded die, 3D IC, all of this. You may use one of them, or you may combine several of them to make a package, and that's a SIP, system in package. And how to do heterogeneous integration. Here we have a toolbox for SIP to realize heterogeneous integration, such as flip chip and wire bonding, molding, die stacking, embedded technology, wafer-level packaging, electromagnetic shielding, and so on. All of this are actually within the regime of electronic packaging. We believe that if the front-end CMOS manufacturing is the most important in the ITRS period, then electronic packaging may be more fascinating and will play a more important role in the period of heterogeneous integration. Well, thanks for your attention. I wish this video would make you understand the concepts in electronic packaging better. Thank you.